Hey YouTube, so today I'm going to do problem number 73 from chapter 4 from the section on Norton and Thevenin equivalent circuits. So just a reminder, a Norton equivalent circuit is a circuit that takes a look at a load, some load A, B, and simplifies a complex circuit into two simple elements, which is an independent current source that is made up of the short circuit current flowing through the load in parallel with the resistance seen by the load. So in parallel with whatever the load is seeing. So it's a simplification of complex circuit into two circuit elements. Okay? And a Norton equivalent circuit is the same thing, except for instead of looking at instead of being the short circuit current, it's the open voltage, the voltage seen by the load. So some V Thevenin, and so when you open the load, it's going to be that voltage source, and in parallel or in series with our Thevenin. So that's the Thevenin equivalent circuit, and they are just simply source transformations of each other. So that's in summary what we're looking for in this problem is that version, the Norton equivalent circuit. So let's go ahead and do that. Your primary tools in doing this is mesh, KVL and KCL. So you have a choice, and what I went with in finding the Norton equivalent circuit is I went with the mesh method because I just like it better. It's everybody has their thing, and that's my thing. So I went ahead and I shorted the load, and then I decided that I would find the Norton equivalent circuit by finding this I short circuit, and that would be the first part of the problem. So let's go ahead and do that. First, let's describe the circuit. We have a 40-volt independent voltage source in series with 2K. And we have 20K here, 5K, 50K, 10K, 40K, and some dependent current source, 30I delta, that's controlled by the current through this 20K resistor. So let's go ahead and start naming our currents. So in this mesh, we have some IA, and in this mesh, we have some IB, and in this mesh, we have some IC, and in this mesh, we have 30I delta. Okay, so let's go ahead and write our mesh equations. So mesh at 30I delta is going to give me some voltage drop here, which I'm going to call Vx. So the direction of the voltage rise is here, minus to plus Vx. So I have minus Vx plus 10K, that's times 30I delta, minus IC. All that is equal to 0. And then my mesh equation at IA is minus 40 plus 2K IA plus 20K K times IA minus IB. All that is 0. My mesh at IB is 20K times IB minus IA plus 5K IB plus 50K times IB minus IC, that's equal to 0. So my mesh at IC is going to be 50K times IC minus IB. IC minus IB plus 10K times IC minus 30I delta, and then plus 40K times IC minus short circuit. That's equal to 0. And then lastly, at my mesh equation at I short circuit is 40K times I short circuit minus IC is equal to 0. Okay, so let's go ahead and build our matrix. We need one more equation because we have 1, 2, 3, 4, 5, 6 equations and only 5 equations and 6 unknowns. So our final equation is going to come from the constraint equation, which says IA minus IB is equal to I delta. And we're going to bring all the unknowns on one side, and that's going to be IA minus IB minus I delta is equal to 0. So now we have a 6 by 6, 6 equations and 6 unknowns. So let's go ahead and make our matrix. So we have IA, IB, IC, I short circuit, VX, and I delta. Constants on this side. Alright, so let's take an inventory of coefficients. The first equation we have -1 for Vx. And then for I delta we have 10k times 30. And then we have -10k for IC, and then zeros everywhere else. The next one is -40, which is going to be positive 40 here, and the constants, and then 2k for IA, and then plus 20k for IA, and minus 20k for IB. Zeros everywhere else. Our third equation will be 20k for IB, -20k for IA, 5k for IB, 50k for IB, -50k for IC, and zeros everywhere else. So that's mesh at IA, IB, and then, so mesh at IC gives me 50k for IC, -50k for IB, plus 10k for IC, and then for I delta we have -30 times 10k, and then plus 40k for IC, and then -40k for I short circuit. Zeros everywhere else. And then at I short circuit we have 40k for I short circuit, and then -40k for IC. Zeros everywhere else. And lastly, for our constraint equation, we have 1 for IA, -1 for IB, -1 for I delta, zeros everywhere else. Okay, now I want to verify you guys can see everything, and looks like you can't see the last line. So here, lower it so you can see the last line of the matrix. There's the snapshot of that. Okay, so now I need to raise it because I don't really have good enough technology really. Okay. All right. So now we're going to use our simultaneous equation solver. We have 6 equations and 6 unknowns, and the first line is 0, 0, -10e3, 0, -1, 10e3 times 30 and 0. 2e3 plus 20e3, -20e3, 0, 0, 0, 0, and 40. Third line, -20e3, 20e3 plus 5e3 plus 50e3, -50e3, 0, 0, 0, 0. Fourth line is 0, -50e3, 50E3 plus 10E3 plus 40E3, negative 40E3, 0, negative 30 times 10E3 and 0. 0, 0, negative 40E3, 40E3, 0, 0, 0. Then last line is 1, negative 1, 0, 0, 0, negative 1, and 0. Solve. Okay, let me make sure. 13.6, 12.96, 14, 14, 52, and 640. Okay, so I got the same answer that I got the first time. So let me post what you should have got when you solve this matrix. So what you should have got is, you should have got IA is 13.6 milliamps, IB is 12.96 milliamps, IC is 14 milliamps, I short circuit is 14 milliamps, Vx is 52 volts, and I delta is 640 microamps. So that's what you should have got when you solve your simultaneous equation solver. And this is the first half of our Norton equivalent circuit. The second half is the Thevenin resistance. Now, we would really like to just be able to disable the power sources and then see what resistance is seen by the load. But we can't do that because the reason we can't do that is because it only works with independent power sources. When you have a dependent power source, it does not work. So now I'm just going to change something. I'm going to open this, open the load, and then my R Thevenin is going to be my V. So the way that we have to find this problem is we have to do it. The R Thevenin is equal to V Thevenin over I short circuit. That's how we're going to find R Thevenin. That means we need to find V Thevenin. And if I open the load, my V Thevenin will be the voltage drop across. So V Thevenin is actually equal to the voltage drop, V40K. So that voltage drop. So I want to find that voltage drop, and that voltage drop is basically going to be 40K times my IC if I open the load. So now I'm going to redo the mesh method. So I'm going to park my I short circuit value over here because that's one half of the problem. So I found I short circuit. That was 14 milliamps. Now I'm going to redo the mesh method, and all my equations will look almost identical, okay, except for now I've opened the load and I'm looking for the voltage drop across the 40K resistor because that is my V Thevenin. Okay, so let's go ahead and redo this. It looks almost identical. So at 30, I delta is going to give me minus Vx plus 10K times 30I delta minus IC. That's equal to 0. So at IA, we still have negative 40. We still have plus 2K IA. We still have plus 20K times IA minus IB. That's equal to 0. And then at IB, we still have 20K times IB minus IA, and still got 5K times IB, and still got 50K times IB minus IC equals 0. So at IC is what's different. So now we have 50K times IC minus IB plus 40, or 10K times IC minus 30 I delta, and then plus 40K IC equals 0, and then that's the different equation, and then we still have the same constraint equation, and that constraint equation is IA minus IB is equal to I delta, but we're going to put all the equation or unknowns on one side and say it's IA minus IB minus I delta equals 0. Okay, so now we're going to make our matrix again, and we got IA, IB, IC, I delta, and Vx. So now we only have 5 unknowns and 5 equations, because we no longer have I short circuit. So let's go ahead and inventory our coefficients. We got 1 for IA, -1 for IB, -1 for I delta, and zeros everywhere else for the constraint equation. So at 30 I delta, we have -1 for Vx, 10K times 30, so 10K times 30 for I delta, and -10K for IC. And then zeros everywhere else. And then at IA, we have -40, which is going to be positive 40 on this side. And then we have 2K for IA, and 20K plus 20K for IA, and -20K for IB. Zeros everywhere else. And then at IB, we have 20K, and then minus 20K for IA, and then 5 plus 5K, and plus 50K for IB, and then -50K for IC, and zeros everywhere else. And then at IC, we have 50K for IC, and -50K for IA, for IB, and then plus 10K, and for I delta, we have 10K times -30, and then another 40K for IC. And then we have zeros everywhere else. Okay. So it's a little out of view. So we'll do that. Give you guys a second to take notes. All right, so let's go ahead and enter this into our simultaneous equation solver. Actually, I'm just gonna use, okay. So we have 5 equations and 5 unknowns. We got 1, -1, 0, -1, 0, and 0, 0, 0, -10E3, 10E3 times 30, -1 and 0, 2E3 plus 20E3, -20E3, 0, 0, 0, and 40, and then we got -20E3, 20E3 plus 5E3 plus 50E3, -50E3, 0, 0, 0, 0, -50E3, 50E3 plus 10E3 plus 40E3. 10E3 times -30, 0, 0, and solve. Okay, I'm gonna double check my answer. .87. Okay. Okay, so I did get the same thing as before. So what you should have got when you solve this matrix, you should have got IA is 8 milliamps, IB is 6.8 milliamps, IC is 7 milliamps, I delta is 1.2 milliamps, and Vx is 290 volts. So that is what you should have got. So we were really only interested in IC because we need to find Thevenin. And we said Thevenin is really the voltage drop across that 40 ohm resistor. So Thevenin is equal to V40K, which is equal to 40K times 7 milliamps, which kilos and millis cancel each other out, so that gives me 280 volts. Okay? I needed that information, but I'm looking for R Thevenin. So R Thevenin is V Thevenin divided by I short circuit. So that's going to be 280 volts divided by 14 milliamps, and that should give you 20K. So 20 into 14 goes 2 times, and then the milos will come, minus 3 in the denominator will come up as kilos. So that gives you 20K. So in that case, now I have all the information I need to draw my Norton equivalent circuit. It's I short circuit, which is 14 milliamps in parallel with R Thevenin, which was 20K. That's Norton. And to find the Thevenin is just a source transformation, but we already found V Thevenin in order to find R Thevenin, and so just so you know, they're source transformations of each other, and then we found that that was really 280 volts, and we know R Thevenin is 20K. Okay, you guys, I hope this video was helpful. Be sure to like and share and subscribe. All right.